That is the creation of the camera in NGL. So the camera hasn't changed too much, to be honest. Just a few name changes with some of the methods. So to create an NGL camera, we need to basically create a vector to specify our from position, our to position, and our notion of upwardness in our world, so the camera can calculate the correct UVN vectors. We then construct a new camera, and in this case set from, to, and up, and say it's a perspective camera in this case. And then next we set the camera shape, so we've got a field of view, our aspect ratio, near and far clipping planes, and again we pass in that it's perspective. That's something that one day I will change because there's a bit of repetition of code there. The only thing that's different in this case is how we pass the camera sort of values to the shader. And in this case, the viewer position is basically where the camera eye is, and that's used as part of the calculation for the half vector for our Fong-Blin calculations. So we literally pass this to the shader. It's a 3F, we want viewer position, and we make a call to camera.getEye, and we access the X, Y, and Z attributes, and that passes it to the camera. What also has changed, the resize method. Previous versions of all the NGL demos, every time resize was called, we had to activate the shader and pass in those values, because the old shaders used to basically have the model view and perspective matrix loaded in here. So we'd have projection matrix, view matrix, and model matrix, and then I very lazily calculated everything in the shader. And so we used to, every time the projection was changed by changing the size of the screen, we used to have to reload it to the shader. This is no longer the case because we actually pre-calculate all of these matrices and then load them to the shader, because that is far more efficient in the sort of modern OpenGL context. So basically the only GL call we make is the call to setting up the viewport, and then the camera shape is loaded on a per frame basis to our shader. The next real big bit of code is our PaintGL, which is basically our drawing routine that's called once a frame. The first thing we do is clear the color buffer and the depth buffer. That's going to just blat our screen back to 0, ready to use. Next, in this case, we're not actually changing our shader all the way through, but it makes no harm to actually specify which shader you want to use for drawing. So the first thing I do, I grab an instance of the shader library and just activate my Fong shader to make it the currently active shader. Next, I'm creating an NGL transform, which is basically going to store, in this case, our global rotation, model position, and translation, which is the mouse rotation and our scale in and out, our zoom in and out, and our translate in the X and the Y. So this is used when we run the program and we use the mouse to tumble. We use the right mouse click to translate, and we use the scroll wheel to zoom in and out. We'll just demonstrate this now once the program runs. Normal mouse click does our rotation, right mouse click is our translate, and then the X and the Y, and then the scroll wheel zooms along the X and the Y like that. So all of this is calculated by modifying the spin X, Y face and the model position parameters, and that is then loaded to the transform stack. The transform stack has several parameters. One of them is a global matrix, which just makes it easier to calculate global positioning of our entire scene, and then we've got the local positioning, which is on a per object basis, a bit like the way XSI uses global SRT and local SRT, scale, rotate, transform. Next, we are grabbing an instance of the VOA primitives class, and We are then calling this method. Now this is slightly different from the previous versions. The previous versions, what we would have done is just loaded to our shader the different values that we needed. So in this sort of case of an old NGL demo, what we would have done is we would have done something along the lines of this, where we would have set our transform stack here, then we would have set shader parameter from matrix, model matrix, and we would have grabbed from the transform stack the current and global matrix and loaded that through. What we now do instead is I have a function called load matrices to shader, which encompasses a lot of this. So what this does is it creates, and this is 4 matrices here that we create. We've got a matrix MV, which is going to be our model times our view matrix. We've got our MVP, which is our model, view and projection matrix. We've got M, which is just our model matrix. And then we've got this 3x3 matrix, which is our normal matrix. And what the normal matrix actually is the rotation parts of our model view matrix. And what we have to do is we take those elements and we calculate the inverse of that matrix and we load it in. And that's used for calculating how our normals must be transformed in our local world space to get correct scaled normals, and this is the equivalent to a call to GL normal matrix in the old style OpenGL. So the first thing we do, M, which is just our current transform matrix, we make a call to the transform stack, we get the current transform, and we grab the matrix and we store that in M. Next we get our model view matrix, and that is calculated by getting the view matrix from our camera, so this is our viewing transform, and we multiply that by our current modeling transform. So this is what the transform stack has done when we've set position, rotation and scale. And this is going to be used for various transforms in the shader, which I'll show you in a second. And then finally we calculate our model view projection matrix, which is basically taking the previous model view matrix here and multiplying it by the projection matrix, which is basically our camera shape, our viewing volume, our field of view and everything else. Next we need to load these to the shader. So these calls here will load model view to the uniform MV, model view projection to the uniform MVP, the normal matrix gets loaded to normal matrix, and M gets set to M. And if we look through at our Vertex Shader, what we should see is that these are replicated here. So we've got our uniforms for each one of those, and we then calculate our fragment normal, so this is our transform normal, by taking the normal matrix and multiplying it by the in normal, the normal that's passed in from our model. Next we've got a flag that we can set to say whether or not the data that's being passed in is normalized. If it's not, then we just normalize it. Obviously this is going to slow things down because it has to make a call to normalize, it has to calculate a square root. So if we've got pre-normalized models and pre-normalized normals being passed in, this should make things quicker if we disable this. But this replicates the use of GL normalize in our code. Next we calculate the transformed vertex position. So GL position, which is the output of this shader being passed to the fragment shader, is calculated by taking the model, view and projection matrix that we've already calculated and multiplying it by our in vertex. Now, as our input vertex is actually a vec3, we have to construct a vec4 so that we set the W parameter here to 1 so that we actually get our correct affine transforms. Next we calculate our I coordinate, and that's calculated by taking the model view and multiplying it by the invertex. So basically this is transforming the I-coordinate into local space, not taking into account projection. And as you can see here, the other matrices are all used to calculate certain things. So for example, the world position is calculated by just taking the modeling transforms and multiplying our invertex. And then this is used to calculate the I direction, which is then used for the calculation of the Blin-Phong half vector. When we go into the fragment shader, we can then see that this is used to do our normal ASD style lighting. So we normalize, we get our E vector, our light vector, our normal vector. We can then calculate the Lambert term by taking n dotted with L. If that's greater than 0, that means that we have some light contribution. We can go through and combine our diffuse with our Lambert term, our ambient, which is just added through. We can then calculate our half vector from normalizing half vector. N dotted with the half vector is equal to the maximum of the dot product of n with the half vector, or 0. So this is giving us our basic Phong-Blin specular term. And then we can calculate the specular contribution by taking the specular material, the light specular color value, and multiplying that to the power of n dot v and the material shininess. So it's a standard sort of dot product lighting system. And this is effectively called every frame that we draw. Every time, if we were to, for example, draw another object in our scene, we would have to set values in the transform stack, load those matrices to the shader, and draw again. So for example, if we wish to draw another teapot, we'd have to do an M transform stack dot push transform. That's just basically going to push our current transform. If we then do a pop transform, this helps to do both at the same time, and I tend to just create some local scope when doing that. Now what I can do is M transform stack dot set position. Let's move this -1 in the X, 0 in the Y, 0 in the Z, and actually let's do 2, and I can also then do a scale, M transform, transform stack dot set scale, and what I'll do is 0.5, 0.5, 0.5, so we're half the size of it. Now I need to load that value to the shader, so I'll make a call to the load to the function. It will recalculate each of these matrices, and then I'm going to make a call to draw. And what that should hopefully now do is draw a second teapot which has been scaled by 0.5, and it should be positioned at -0.2 in the X. So when we draw it, you can now see that I've got that second teapot there. And what you should also notice is, because it's been scaled, because we're calculating the normal matrix correctly, we are still getting similar sizes of highlights and everything else. And this most probably highlights the most of the changes in NGL. And this is documented in the source, and as I say, there will be lecture notes coming up with all of these things explained. So keep an eye out on either the CA2 or the MSc websites, and you will see all of these things. And I think that's it for now.